Trying for the stream. Check, mic check, mic check. Yes, no, maybe so. Check, mic check, mic check.
If everybody could get seated, we're going to get started in just a couple minutes. So if everyone could grab their last plate and get seated. Okay, thank you, everybody. So today we have a talk from Diana. She's going to be talking about networking for state-of-the-art ML. This is definitely one of our more technical talks. So please feel free to, take notes, do whatever you need. If you have any questions, whether they're asking her something about her presentation here or clarifying questions, we're going to be doing questions throughout the presentation. So do feel free to raise your hand whenever. And then wait for me to come around with the audience mic just so the lovely people on the stream can hear you. Just some housekeeping notes. If you have to go to the washroom at any time, please exit through these glass doors, go down the hall and to the right. That's where the washroom is. If you need to take a call or do anything similar, don't go this way. We will be able to hear you if you go this way. Go this way, and ideally even go right in front of the washroom. We won't be able to hear you if you go all the way down the hall and then make a right in front of the washrooms. Just to give you a little note, I think that most of you have been to a Trajectory Labs event before, or if not, are a part of our community, but I'll just say this anyways. Trajectory Lab is an AI safety nonprofit. Our mission is about making AI go well, and specifically helping Toronto unlock its potential in making AI go well. We do this through running events like these. We also do this through a peer network, which means if you're interested in AI safety, you should talk to someone from around the lab. We have opportunities like fellowships and hackathons and summer intensives, as well as co-working space. That's another thing we provide, co-working space. So if you're interested in AI safety in any capacity, whether it's our events, our office space, or our opportunities, please do stick around afterwards. Talk to Diana about her presentation, talk to us about our community. With that being said, I'm going to hand it off to the lovely Diana. I hope you're all excited to see her presentation.
Thank you, Georgia. Thank you all for coming. Today we'll be talking about networking for state-of-the-art ML, and we're going to touch upon some implications for technical AI governance that are related to networking technologies. So what would I like you, my dear audience, to take away from this talk is, if you're the infrastructure team, probably you want to know how networking, these networking details to make your infrastructure run the training runs faster. If you're yourself training models, understanding network and interconnect limitations of your training infrastructure goes a long way in terms of identifying bottlenecks and can give you an idea of what sort of practical optimizations you may want to look at. And if you're in this handful of people that are interested at the niche of exploring interconnect bandwidth limits related to technical governance policies, this talk is for you. So, a bit about myself. I'm a network engineer by day. I'm also currently doing a SPAR research sprint under Aaron Scher's mentorship. And we're essentially working on this very fancy problem called networking interconnect limits as a mechanism to verify international agreement about AI development. The basic idea is that in the future we want to have some sort of international coordination between states where each party can prove and verify if any other party is training dangerously large or dangerously capable AI. So what does network bandwidth has to do with it? We're trying to see if go back, please. Okay, I guess the slides didn't show up. Anyway, so the main question we're trying to answer: can network traffic patterns serve as a proxy for compute usage? Could the orgs report or limit network traffic to prove they're not running dangerously large training models?
Sorry.
So Thank you. Appreciate it. Yeah. No. Oh, no, they're here.
Oh, they are there? Okay. They should be good, actually.
Okay, perfect. We are good. So the main idea is, yes, please. Thank you. So the main assumption is that you have, when you train very large models, it produces a distinct network, like a traffic footprint. So for example, here you have like a small comparison of training versus inference run. The main thing is that the traffic size being produced for large models, it can be hundreds of gigabytes, if not terabytes, being exchanged between the pods, versus say inference workloads, you're dealing with magnitude of megabytes. So you have this very, very distinct signal that you may be doing a large training run. And just based on that very simple metric, we can set some sort of policy saying that, hey, if you can prove that you're not using bandwidth above this threshold, we trust that you're safe and you're not going to train large dangerous models. Now, when it comes to actually enforcing this policy, here's two practical questions you want to consider. So what is this violating training traffic pattern or signature that we're looking at? Or like what exactly should be the bandwidth limit threshold above which the organization is considered dangerous? And where would you place this limiter or this monitor for this governance mechanism? So last piece of context on the talk. As past few weeks, we've been trying to answer these questions, and turns out that there is no really such thing as a typical training cluster or typical training workload, mainly because major GPU providers, they have different philosophies, they have different network topologies. I found it pretty hard to find public detailed reports on topologies, maybe because they're not fully published yet or they're being secretive. So this talk is really a compilation of what I found over the past month from the conference presentations, cloud documentation, and third-party reports. So let's jump to it. This is the overview. We'll be okay. This is the overview. We're gonna go through a little primer of what is a training workflow, what are the parallelism types, some network terminology. Then we're gonna dive into the two main network designs, and we're gonna comment on governance implications of what we found. So for ML training 101, we're gonna take just your classic hello world, your neural network training step. You have forward pass, calculate the loss, backpropagation, and then you update the gradients. The main characteristics I want you to focus on throughout the talk is number of parameters of the model. So that directly relates to kind of the network footprint. For example, for state-of-the-art models like Llama that is trained on, that has 800 billion parameters, if you translate it to the size, if you encode every parameter with 2 bytes, that translates to terabyte, over a terabyte of model size, and that really determines the volume at the traffic volume at this gradient update stage. And then other factors are the parallelism factors. So you can partition your model across multiple GPUs as an example, and you can slice and dice it in different ways. That essentially determines the frequency and volume of the interstage communication. So anything before the parallelism level, you're exchanging, with our example of 1 terabyte size model, we're exchanging 1 terabyte of gradients every step, so every second. Every second is really not that frequent, and latency requirements are low. So we're going to say this is a yes. That's a great question. A step is, I'm defining a step as so that previous diagram that we saw, the forward, more about this than I do. So please correct me if I'm wrong. Essentially, 1 second is an acceptable latency for this layer of parallelism. Sounds good? Okay. This room has a lot of way more qualified people than I do, so please stop and comment or correct me. Then you have tensor parallelism. You split individual layers across the GPUs. So modern models, they take a lot of space. They can be all loaded into a single GPU, so you partition it. So now you can partition it, load it into a GPU. However, the trade-off is that you now need to do multiple sync operations. And I think roughly that's about multiple or 4 syncs inside the forward pass, in addition to the sync inside the back propagation. And here, the tensor parallelism has pretty high latency requirements. So if you want your model training with tensor parallelism to finish within your lifetime, you really want this sync operation inside the forward pass to take, microsecond or sub-microsecond latency, and the volume you're exchanging is about, spans tens of gigabytes for large models. So tensor parallelism has the highest latency requirements. That's all you need to take a note about. And then last one is pipeline parallel. I'm sorry, was there any questions? No, we're good. So pipeline parallelism, you essentially same thing, but you split it vertically. You split the models across. You split the model layers across the pipeline stages, and you're essentially forwarding the activations between each stage. The also pretty high latency requirements, microsecond, sub-microsecond latency, but you're exchanging less volume of the traffic, so in terms of hundreds of megabytes with our example. Now, you can combine them, yes? Yes. Good question. You can combine, as I understand, state-of-the-art model training, you combine all of these, and that maps pretty nicely with kind of DC cluster terminology. So you have each of those yellow boxes is a node with 4 GPUs, and you can see there within each node there's tensor, and then between nodes you have pipeline parallelism, and between kind of you can consider the blue regions over here as a pod, and the data parallelism maps to kind of interpod communication. If you take kind of standard DC networking topology. So in ideal world where you have infinite money, infinite cabling capacity, you have everything connected by low latency fiber, but later we'll see the costs just explode with each layer. So what you want to have is the fastest, most expensive low latency links for tensor parallel level. So that's high bandwidth, high frequency. So this is, you can think about this is your NVLink layer. And then you have lower bandwidth, but also high frequency for pipeline parallelism. So that's your InfiniBand links. And for the, you can use the cheapest, lowest frequency copper Ethernet cabling for data parallelism because of low frequency, low latency requirement. And you can see like you have seconds, microsecond latency, data parallel gradient sync usually dominates the wall clock time, and we'll talk about it later. There's also a thing called expert parallelism, which I am least familiar with, but it's a way to further partition your model so that you're spreading it across multiple different experts. And here, as I understand, the challenge is that you have non-uniform traffic distribution where different tokens can be routed to different GPUs, and you're also doing exchanges or this routing multiple times per each MOE layer. You have still pretty high latency sensitivity and highly variable bandwidth pressure. There's also sequence and context parallelism, but we're not going to cover it in this talk. So in a summary, really we just want to look at the latency sensitivity over here. So all these different types of parallelism, they ask for, they have different traffic patterns, so they ask for different network technology. Really, the most expensive ones are the tensor parallelism column. It like that really drives up the cost the most. And the other types can tolerate lower latency switched fabric. So here's some, yes. Can I explain pipeline? Pipeline bubbles. No, I can't. Thank you, Claude, for generating content I didn't review. Network terminology. So last thing, networking people love to add their own terminology, so we're just gonna go through it real quickly. We have scale-up network. So this is your scale-up network is, you can think about tensor parallelism layer. You have, this is your direct GPU to GPU interconnects. Scale-out network is, well, anything outside is your fabric that connects nodes and pods. Then in DC networking you have pods or islands, which is a group of GPUs connected by high bandwidth fabric. Really, every company has their own definition of a pod or an island. And all these three things, they make up what's called a backend network. And there's a front-end network that we don't care about for this talk. This is just standard Ethernet, usually for connecting storage to your training model. Also, network used for control plane management traffic. And just a reminder, we're purely talking about training clusters. Yep, most of the GPU providers, they gonna have different training and inference clusters for security reasons, but also they have more relaxed SLA commitments, different hardware, different topology for inference cluster compared to training clusters. Difference between the two clusters. Sure, so anything that's not covered on the slides, is there? Oh, okay, so say, like, pick your favorite model provider. Say Gemini. We like Gemini. So Google has one cluster for training Gemini and one cluster for serving inference for Gemini. So you're interacting with the inference cluster when you're prompting Gemini. And the internal Google team is going to use, their internal training cluster to train train Gemini, essentially. Does that make sense? Okay, cool. So let's get to the meat of the presentation. What are the different network designs? And this is really my terminology and my taxonomy. I generally see two paths. One is you take whatever NVIDIA recommends and call it a day, or if you don't want to, you essentially just like throw a lot of money into your network infrastructure, and everything works. However, if you want to get yourself out of the NVIDIA's grip, you build your custom topology, you pay, and main characteristics you want to look at. You have scale-up domain, which is the domain where each GPU is connected to each other directly. You have about 8 GPUs in the scale-up domain, and then the pod size is going to be 4K GPUs per island, and you have 8 islands per cluster, so makes 32K GPUs total. The main things that for interconnect, they only use NVIDIA NVLinks between those 8 GPUs. Everything else is RDMA over Ethernet. And that's nice because Ethernet cabling is the biggest contributor to cost. And if you like majority of the network is Ethernet, you're really saving up on expensive InfiniBand links. One key is that you have 7-to-1 oversubscription rate at the top. So each of these, for every 7 gigs coming into this layer of the switches, you only have 1 gig coming out into the spine switch. And that's fine because you're essentially doing tensor parallelism here, and then between the nodes you're doing pipeline parallelism, and then every 1 second or so you need to reach the spine switch for data parallelism. And 7-to-1 oversubscription works because not every GPU is gonna talk to every other GPU all the time. Does that make sense? Okay, questions? Yes? Fair. Yeah, I think one of the key advantages of this design is that you're really not deviating much from Meta's existing DC design, which means that all the expertise, all the tooling you have for managing DC networking, you can transfer it here. So that's actually a great question. The next slide is from Meta's paper on how much network and switches failure contribute to interruptions in training runs, and they share numbers 8.4 on their Llama paper, which is pretty low percentage if you consider all the number of switches and number of links, and they're all like commodity cheaper commodity switches. You have a lot of them, they add up to something is going to go wrong if you have enough of them, but they have really good monitoring and configuration management failout infrastructure to manage these failures with. They can essentially afford commodity switches because they have a very strong network engineering team and infrastructure built for managing the network. So yeah, not everyone can afford it. Okay, this is this is what NVIDIA recommends you have. So it's called rail optimized, or I think it's also referred to as InfiniBand topology. You essentially have every GPU connected to 8 different leaf switches, and such that each GPU can talk to any other GPU just only via 1 switch hop away. So pretty nice. Every GPU is connected to every other GPU. The caveat is that so advantage is that you have all-to-all collective communication that is heavily used in, as I understand, MOE, like mixture of experts, parallelism. So it's pretty nicely optimized for that. However, the main disadvantage is the cost. So the cabling, and you have maintenance issues because cables are of different sizes. You have leaf to spine distances that are greater than 50 meters. And compared to copper cables, these optics, they run hotter, they use more power, and because of that, they're more prone to failure. So they generally flap more because of that. But if you don't have a good networking team, or if you don't invest into a network team, this is pretty much your only option. This is what most neoclouds use, and as I understand, Microsoft uses too. So just to give an example of the difference between standard class topology to rail optimized, you see the networking kind of explodes at the spine level. Let's just take a note on just how expensive this design is. NVIDIA's CUDA mode, NVIDIA's mode really extends far beyond chips and CUDA. They also own interconnect technology, so all the NVLinks, InfiniBands, protocol layer optimizations, they're entirely, NVIDIA is essentially using it as a vendor lock, and NVIDIA has a power to dictate infrastructure and topology standards too. And there's really no need for all these components to be so expensive. So for example, the NVIDIA InfiniBand transceiver, it can cost up to $3,000 per transceiver. That's a 4 or 5 times the markup of any other transceiver. But they can set those prices just because they have the monopoly, just because they can. So you have 3,000 per transceiver, you have 64 ports, you need 64 of them. You need hundreds of switches. With these 64 transceivers, the costs quickly add up to $300,000 for fully connected switches. And that's significant. So what does it take to break out of this vendor lock or the mode? And it takes quite significant effort actually. So you have Google, who manufacture their own silicon, manufacture their own interconnects, who go to the length of creating their own bespoke protocols at the layer 2, layer 3 level. But that cost of hiring developers, network engineering team, and all of the above, it still justifies the savings they get by not using NVIDIA. So this is their topology. This is what they use for a training cluster. So this is called a torus topology, where maybe let me give you a better picture. Essentially, each circle here is a GPU, and they're connected in this 3D cube. And it's so essentially in this cube, Google assigns different torus dimensions to different parallelism strategies. So you can have tensor parallelism running along the x-axis, pipeline parallelism across y-axis, data along z-axis. And this is where it breaks out of the terms, like the scale-up term. It doesn't really fit the definition, but because torus rather than switched all-to-all, chips doing tensor parallelism across opposite corners of the cube, they need to traverse multiple hops. So it scales better, but it's not as good of an all-to-all parallelism pattern, just because, say you take this GPU and this GPU, you essentially need to make 6 hops to reach that GPU. So all-to-all communication, not that great, but it's worth it just because you can scale to up about 9K of such TPUs inside a pod. So before you hit the copper Ethernet fabric, you can have 9,000 TPUs connected by low latency, high bandwidth optics. So this main trade-off is all-to-all flexibility for lower cost and better scalability. And AWS Rainier, they use similar fully meshed topology. I think they go further and do something with 4D, like 4D torus, so they add an extra dimension. So, okay, here are all the main network designs. How does it relate to technical governance? And as a reminder, we think our claim was that monitoring interconnect bandwidth between GPUs is a cheap, low robustness, software-only confidence building mechanism that could be deployed quickly as a stepping stone toward more comprehensive compute use verification. So it looks promising because it has software-only, so it's cheap, it's non-invasive, and it's easier to deploy as compared to more involved on-chip verification mechanisms. However, you have answering the questions of where do you place the limiter is I think we ended up with more questions than answers. So it really monitor limiter placement must be tailored per topology because there's no universal choke point. And there's no I don't see a single training traffic here because different providers, they run different strategies. They have different optimizations for their training runs. It's hard to define the traffic signature. So you have Google that can pretty much run the entire model training run inside a single pod, inside those 9K TPUs. That's going to be different for network traffic produced by, say, Metis network. And then we haven't covered topology. We haven't covered the algorithmic improvements that may completely bypass the limit. So there's work in gradient compression and async updates that can reduce the bandwidth footprint by multiple orders of magnitude. So they potentially can evade bandwidth monitoring entirely. In terms of kind of picking, compute governance kind of has a nice single metric for defining what is a dangerous cluster by this many of flops. If the cluster has this many of flops, it is capable of certain things. I think for networking it's not as straightforward, but I guess the one takeaway is you can probably use scale up to scale out ratio as this one single metric that can give you an idea of like a quick idea of what the topology is like. So you just divide the scale up bandwidth by the scale out bandwidth. So with, for example, with NVIDIA's example, this ratio is 18:1, which means that crossing the scale up boundary or going to copper Ethernet is 18 times more expensive than within the pod. And then Google's and Amazon's low ratios like 6:1. You have a softer boundary. You have more flexibility with tensor parallelism there. The ratio itself by itself is not complete, so you really need to consider the domain size, the latency, and the topology. The ratio just tells you the penalty for crossing the boundary. But if you want to get more detailed view of the network pattern, you really need to know the domain size to see how often you need to cross the boundary. And then latency and topology tell you how much it actually hurts in absolute terms. And I think that's it. Thank you for listening, everyone. I'll open it for questions.
Thank you. Does anyone have any last questions?
Channels.
Oh,
So what we're imagining here is someone builds a huge data center, says that they're not going to use it to train a big AI model, and then maybe they are, maybe they aren't, and we want to use this network governance to sort of determine that. What kind of other things might they be using the data center for, and what are the network traffic patterns of those going to look like? That's going to be different.
Oh, I see. So I guess one scenario is maybe the prover is saying, hey, we're only using this cluster for inference. But if the network monitor, if the network reports say otherwise, we can catch them red-handed and say, hey, you're not using it for inference, are you? But really, I think the more plausible direction with this is use it not as a strict enforcement, but as a, I think the right term is confidence building mechanism. So it's a low effort, low stakes things organizations can commit to, because like reporting network traffic is really, it could be anonymized. It doesn't take much to report network traffic. As a stepping stone for more robust mechanisms for compute governance. Yes.
Sorry, potentially very naive, but aren't you also using different chips depending on whether you do training runs or run inference? And wouldn't that be easier to track than these very, at least to me, very complicated calculations?
Yeah, for sure. The clusters are different. The hardware is probably going to be different too. I think network bandwidth just acts as a nice proxy for compute usage to be used in addition to, on like more concrete on-chip reporting governance mechanisms. Does that make sense? Just because it's like this method is just cheap to implement.
And sorry, I'll follow up if you don't mind. Would this all depend on self-reporting, or is there a way to sort of like externally get access to this information somehow?
We're exploring both, like self-reporting, and if a third party can come in and do the measurements, but we still haven't figured out, how exactly would they do it? Like, at what point would they measure it? Because putting network monitors at every link is probably going to be not feasible or too expensive. So, like third-party checking implications are more involved. We're still thinking through that.
And is there a correlation with energy usage that might be perhaps more easily monitored from an external perspective?
Yeah, for sure. I think for training runs, you need a lot of optics, and those optics they consume more energy than copper connects. So yes, I think translates well to energy too. G.
This might be a really naive question, but why else would someone build a really big data center stuffed full of GPUs? Because I'm thinking the cost of building a data center and centralizing all those GPUs starts to become non-linearly high, because you have to concentrate all the power and also the battery usage. And these days, if you're XAI, like a whole bunch of gas turbines, right, in one place. So what would do these hyperscalers actually have a motivation for building very large data centers with lots of GPUs other than to do very large training runs?
I'm not up to date with the state of. You're asking about decentralized training, and no.
No, it's a really naive question.
Okay,
I don't know the answer, right? Like, why else would you want to build a really big data center stuffed full of GPUs?
Okay, fair enough.
Yeah, other than doing really large training runs.
That's a good question. That's a fair question. I think one implication is maybe governance of existing data centers. Yeah, if your satellite imaging can detect a huge data center, that's probably a more clear, cheaper signal that something is going wrong. Christy.
Did you learn something during this research that makes you more optimistic?
More optimistic. Let's see. To be honest, I think the more I start looking into the implementation and enforcement implications, the more problems I encounter. But I feel like that goes for many governance mechanisms. So I think the ways to, but we're still optimistic compared to other technical governance mechanisms we exploit. This still seems to be in the realm of enforceable, plausible to implement within the next few years. But maybe governance people can tell me, give me a reality check of how plausible this is. Thank you.
Thank you so much for the talk.
Thank you, everyone.
So please do hang out with us for a little while longer, chat, ask Diana some more questions, and get to know each other. Okay, we'll be here, we're usually here until 9:30, something like that, so hang out for a while.